Hey math people, we're at the last lecture of this 3D coordinate system and vector run, first chapter of Calc 3. All right, so what's the deal? What are we doing? We're going to be graphing more than just lines and planes. We're going to be graphing cylinders and generally quadric surfaces, whatever that means. So we're going to start with a warm-up on that. We're going to start drawing cylinders, which is not too bad. We'll look at some familiar quadric surfaces, look at some newer ones, and then just look at the full list. And these are just like what we would expect you to be able to identify like algebraically to visually as a surface. You don't have to be a pro at it, but just like kind of good enough to, savvy enough to kind of figure it out if you need to. All right, remember this video is for you, Freddie. So what that means is to use the timestamps, pause when you need to, make this video efficient for you, not me. For you. All right, so let's build our understanding of space. So we're used to the parabola as y is equal to x squared, but we have more variables in play when we're graphing in space, x, y, z space. So how many different like combinations can you create? Well, you can do like y is equal to x squared, or z is equal to x squared, or y is equal to z squared, or x is equal to y squared, or z is equal to y squared, or x is equal to z squared. These would all be parabolas on their own respective planes. So, you know, of course, we're used to the xy plane. But what would this plane be called? What would this plane be called? So on and so forth. This is just a way of building something maybe sort of obvious in some ways, but remember, it's not when you're dealing with the intersection of three planes in space. So give it a go. 3, 2, 1. All right, so we're just labeling the axes, right? And we're used to graphing, like I said, on the xy plane. The independent variable is x, the dependent variable is y. And it's the same pattern as you'd expect. Here, the independent variable is x, the dependent variable is z, right? So this would be the z axis here. Consider, you know, what that means when I graph it in space, right? So we're used to like y is equal to x, x squared, where are you at? And then I want to just restrict this for when z is equal to 0. Z is equal to 0. Oops. You know, this is just what you'd expect on the xy plane, just your standard parabola. But, you know, looking at like the next one, right? So if we're looking at z is equal to x squared, z is equal to x squared, on that plane, that would make y equal to 0. And take a look at that, right? This is a plane, right? It's just simply on the xz plane, but this is still a curve on a plane. It's just, you know, it looks like this instead of looking like that, right? The xz plane is a different plane than the xy plane. And then you can just do this so on and so forth for the rest of the these, right? Dependent variable being the one on the left side, independent variables on the right. Okay, so that's the general idea, is I could do this 6 times over. 6 times over. Oh yeah, because I can have like a sideways parabola. All right. So if we extend this into space, right, the idea is, well, we just looked at z is equal to x squared, and it looked like this, but this is only when it's domain restricted such that y must be equal to 0. There's no such domain restriction here. So I'll just show b here, just for the sake of, you know, what I'm getting at. You get this shape because the logic is there is no y present here. There's simply no y. So y can be whatever it wants to be. And this equation will still hold true so long as x and z share this relationship. So y can be 4, y can be 10, y can be, doesn't matter, right? Y gets this freedom. So that's why you have this forced shape that this equation establishes for x and z, but y has no impact on the equation. So you get a cylinder that is what we'd say parallel to the y-axis. All right. Well, each of these are going to look the same way, but they're going to be pointing in different directions. So try to establish some sense of grounding here. You can see what they look like. I'm going to do some drawing. So like you would see me sketch z is equal to x squared along the y-axis, right? So it'd be along. Actually, I'm going to orient it in the same way, right? Does it help if I do something like this? I mean, they both look the same pretty much. So yeah, like you can see the way I oriented the x, y, and z axis, x, y, and z. So I'd sketch this going along this y-axis as just a bunch of parabolas extended off the xz plane. Anyway, see what the rest of these would look like. 3, 2, 1. Of course, they all look the same, but they're all kind of pointing in different directions, right? So if I were to do z is equal to x squared, it'd be pointing parallel to the y-axis, but if I do z is equal to y squared, it'd be pointing parallel to the x-axis, right? And if I did x is equal to y squared, you know, same story, right? This would just be parallel to the z-axis, right? And be kind of pointing up in this direction. So you get all 6 of these different shapes. You don't have to be a pro at this, but just kind of acknowledge that these all create the same shape, but just kind of pointing in different directions. These are all parabolic cylinders, right? So the cylinder aspect of it is it's cylindrical along the axis that's not present. So here it'd be along the y-axis. Here it's along the x-axis. Yeah. Okay. Yeah, so these are cylinders, by the way. We use the word cylinder for that. So are cylinders still cylinders? Yes. We just call them something special. We call them circular cylinders. So we're just being a little bit more specific now. That's all. It's just not that I'm going to be like, you know, I'm going to be listening to some Math 2 geometry students in the hall talking about cylinders. And I'm like, hey, you guys really got to specify what kind of cylinders you're talking about. Eventually in Calc 3, we call them. I mean, shut up, dude. Right? Yeah, so, but here's the cylinder that you're familiar with, right? The circular one. So I can just say is equal to 1, right? Still a cylinder. It's just now a circular cylinder. What you can do is you can divide out coefficient by some number, whatever. We'll just make this one 9. You can see this is an elliptic cylinder, right? It was an ellipse on the xy plane, but we're cylindricalifying it to get this shape. And then you can also get a hyperbolic cylinder. So if you remember the hyperbola, it looks like this on the xy plane. And of course, you can do this on the xz plane or yz plane as well. But this is that kind of bird's eye view xy plane. You can cylindrify it, and it would take on this shape, right? Whoa, take on this shape. All right. All right, so do you remember the equation of a sphere? We just looked at cylinder cases. Those were all just cylinders. But there are more quadric surfaces. And we already started looking at one. The sphere is a quadric surface. If you remember the equation of a sphere, 3, 2, 1, here it is. It's just that x squared plus y squared plus z squared is equal to r squared, right? It's just a circle, but with another term, another dimension. So this is also a quadric surface. There are a few more, though. So I want to just define what a quadric surface is generally. It's got to fit the mold of this monstrosity. It looks like it's a crazy equation. It's kind of not. A lot of these will be in practice 0. So like for equation of a sphere, you see only squared terms. Anything that isn't a squared term, all these, right, are 0, and then you have the constant. But anyway, if it fits the mold of this this equation, which like technically these did, right? You just had a lot of zeros, There's no x's, you know, maybe in something like this. There's no x's, no y squareds, no y's, no z squareds. So those coefficients would be 0. But if it can fit the mold of this equation, it is known to be a quadric surface. So we know about the sphere. We know about all the cylinder types: parabolic, cylinder, circular cylinder, elliptic, and then hyperbolic. But what are the other quadric surfaces? There's a few more that we like sort of kind of expect you to know. And we arrive at the shape through this process of drawing horizontal traces to some plane. And what that looks like in real practice, so we're going to just try to build the intuition for these 3. This is a squared right here. This is y squared. Yeah, so we're going to try to build the intuition for these 3 shapes. And the way we're going to do that is by just like plugging in numbers for z. If I plug in something for z, what shape pops out? If I plug in something else for z, what shape pops out? 1, 2, 3, whatever it may be. So like looking at A, right? If I said z equal to 1, z equal to 2, z equal to 3, z equal to 4, what shape would that create on those respective z is equal to k planes? So I'll show this one. I'll show A, right? So we did look at A in lecture 1. It looks like this shape, right? I'm about to show you. See if you can visualize it. 3, 2, 1. Here. If you remember, we called this a paraboloid, and it still is one. But now we're just building a different way, like somewhat of a different way of thinking about it. Not really, but a little bit. Yeah, so if I said z is equal to whatever, k, right? And I just kind of Actually, I can even move this up and down. Let's just go from like 0 to 5, right? You can see here that each of these intersections create a circle, right? You have a circle, no matter how you splice it. You just cut it perfectly parallel to the xy plane. Each of those intersections create a circle, right? And then a more fun way of graphing this would be restricting this for when z is equal to k, right? Yeah, so that's what you get through and through, circles. Well, do the same thing for B and C and see what shapes you get for those. 3, 2, 1. All right, so yes, you get paraboloids for A and B. For C, you get a paraboloid, but it's a specific kind. It's not a circular paraboloid, it's an elliptic paraboloid. And that's because each of the like perfectly horizontal to the and parallel to the xy plane slices, they're all going to create ellipses on those planes. So, but B is a little bit different though. So B is really just pointing in a different direction. We were looking at z is equal to x squared plus y squared, which is a paraboloid where the z pole is inside of it, right? Well, if I just change this up a little bit, I do y is equal to x squared plus z squared. Sometimes I do my squareds that way, but I'll change it. It's kind of like being a little lazy. All right, here we go. We got this shape right here. But here's the thing, right? If you were to create horizontal traces where z is equal to k, you're actually getting parabolas instead. And I'll kind of show that. Can I like copy this, paste it, do z is equal to k? Just doing some stuff. Yeah, look at this. Right? So each of these, right, one more time, I'll say parallel to xy plane, right? Each of these like little cuts create parabolas. Yeah. So it can help you like just plugging in 0 for x, plugging in numbers for x, or plugging in numbers for just y, or plugging in numbers for just z. The general premise of that, drawing traces, two-dimensional traces where you fix one of the variables to be a constant, is not a bad idea if you're like in a rut and you really need to know what the shape looks like. The reality is, I don't really need you to be like a pro. I'm going to name some crazy quadric surfaces just you get ready. If you can just kind of like into it, like just kind of like use your knowledge of space and variables to kind of think about what these may look like, that's totally fine. But I'm giving you a rigorous methodology. If you're totally stuck, and you're like, what in the world could this possibly look like? What direction is it facing? And I think it's a paraboloid, but to what pole? Whatever. Just practice plugging in 0 for y. So those would be, parallel to the xz plane, right? So what would those be? That would be like y is equal to k, right? And then, right, looking at those like intersections, right? Those are all circles along, the y pole, right? Those are all circles, and I can even show that by doing this again. Y is equal to k, right? Those are all circles along the y pole. I don't know. Sometimes I just have fun with the demo aspect of it all. It's like, oh, you know what? I'm just gonna let it rip. Oh my, look at that. Not bad. Not bad. Whoa. All right. And then along, like, let's do the same thing for, I don't know, x. So I would make this. There we go. And you would just get those sideways, parabolas. You kind of like sweep it from left to right, back to forward, and bottom up. And you think about each of those sketches, and then you kind of just take that composition mentally to get what that shape may look like. You can do that. It's just a method of just drawing traces parallel to your plane, x, y, xz, or yz. Okay, so we can do that right now with this. So plug in 0 for x. Think about what shape that's going to be parallel to the yz plane. Plug in 0 for y. Think about what shape that's going to be parallel to the xz plane. And then same thing for the last one. Plug in 0 for z, or not 0, like any k value. It could be 0.2, 3. You just has to make sure it shoots out of a reasonable equation. And then, what would that look like parallel to the xy plane? Actually, speaking of those restrictions, k is actually restricted here in this shape. k must be between two values. And you'll see it really quickly once you start to plug in k for whatever you're looking for and then solving for it. You'll see something a little like, oh, duh. Anyways, think of last thing before I show the graph of this. Think about what this might look like, right? You know what a sphere looks like, but what happens if I do this? Anyway, 3, 2, 1. All right, so when I just like set x equal to k, y equal to k, z is equal to k, I'm left with all these equations. All I'm doing is I'm just scooting over the k expression onto the right side. And I'm thinking to myself, well, the sum of two squares must always be positive. So this expression on the right must always be positive, or 0. You can make this exactly 0. That's totally fine. If these always must be positive, what I'm doing is I'm setting this expression greater than or equal to 0. I'm setting this expression greater than or equal to 0, so on and so forth. If I set each of these greater than or equal to 0, I end up getting these inequalities. And what these inequalities ultimately create is that like scan to left to right approach. Actually, I'll create like a kind of a fun version of this. Yeah, I got some artistic energy brewing right here, right now. So this creates an ellipsoid. It's going to be egg-like. I say egg, but not quite. So look at this. We're going to make a fun little demo together because we just can, and it'll be worth it. Z squared, if I can think. This is like in terms of recording this, I think I'm on this is like the 10th video in a row I'm doing, so I'm at the tail end here. All right, we got this like M&M looking shape thing here, right? If we wanted to make it look egg-like, I make it silver, I don't know. But anyway, here's my shape. What I want to do is I want to, oh, check this out. It's gonna seem kind of random, but it's not. I want to scan it. I want to scan it from left to right, forward, backward, and front, center to kind of see all these elliptic traces, really. So I want to set, this is just when x is going to be fixed to k. This is going to be when I'm going to use different letters for the other expressions because they have different domain restrictions. So, and that's just kind of being fancy, but not really. I'll say this is when y is restricted to j. And then this is going to be when, give me a second here, when z is, we'll just say that's equal to L. All right, you can kind of see what I'm getting at here, right? So if I wanted to scan this, where is this at? Oh, yeah, if I wanted to scan this, oh man, this is looking cool already. Scan this, let's do k. So that would be horizontal, it would be traces that are parallel to the YZ plane. Yeah, they'd be scanning it this way. So that would be from -1 to 1. And you can see here that each of these traces are elliptic, right? And you kind of just scan it forward, backward. I'm going to do the same thing. It's going to be worth. You can already see it's going to be worth it, right? Square root of negative square root of 2. Square root of 2. And then 2. Oh man, this is gonna be great. Anyone else just like, man, let's see it, dude. All right, look at that. Right. So if you do your traces, parallel to the YZ plane, parallel to the XZ plane, and then parallel to the XY plane, you get all these shapes, and they're all ellipses, right? And when they all match in this fashion, I mean, you're going to get a good sense of what the shape's going to look like. It's going to be an ellipsoid, in the same way that if you were to do this identically for a sphere, they'd all be circles. All right. Yeah, so here's a full list of just like all the possibilities that can happen. I'm going to just show, I mean, if you want to think about what they might look like before I show all of them, you can try to do that. 3, 2, 1. Yeah, so here they are. We already looked at the ellipsoid. This is literally it right here. If I just make one of them negative, so I'll make this one negative. Whoa. I actually want to make these all negative now. Oh, cool. Yeah, the domain restrict. Oh, wow, this is crazy. I feel like I can just get hypnotized in this, right? Well, anyway, yeah. If you just make one of them negative, you get a hyperboloid of one sheet, is what we call it. And you can see, you know, we got an ellipse going down, but we have like these hyperbolas. So that'd be an ellipse parallel to the XY plane, but you know, the other two are hyperbolas parallel to their respective planes. But if we go ahead and try out the last one here, so we'll just make this one negative. There we go. You get a hyperboloid, a hyperboloid of two sheets. Are all of them there? Yeah, I think so. Kind of a unnecessary idea. I very, very, very infrequently like study. I mean, this is like the only moment here, people study a hyperboloid of two sheets, you know. But like, yeah, this is what it would look like. I don't, you know, me as your Calc 3 teacher, I wouldn't really expect you to be like a pro at graphing these in any way at all. But like the ellipsoid, this one I'd be able to, I'd want you to be able to graph the cone, the paraboloid, right? So I'm going to do cone right now. Yeah, I mean, why not? Z squared. Oh, so I just have to make this 0 for cone. Yeah. So what's the difference with the cone, right? You'll see here that there's a constant for each of these three up top. You have, you know, the sum of squares, and that's equal to a constant number. Same thing here, just a subtraction constant, subtraction that's a constant. You'll notice that there's no constant within each of these down below. So that's why I just made it 0. So I could scoot some of these over onto the other side if I wanted to. Like, I mean, I'll do that just for the sake of, I don't want it to be too hard to follow. And I don't have to use these same values, but I do like that I'm using kind of like different A, B, and C values, because it doesn't need to be, that's the thing about the cone. They don't need to be perfect circles. It's totally fine that this is like an elliptic cross-section to the XY, parallel to the XY plane. Anyway, I'm just going to go ahead and graph this, and we'll just kind of see this kind of fun idea in action a few times over. Here we go. All right. Cool. Yeah. So it's like a hyperbola here, and then it's an ellipse in this direction. There it is. I was wondering where was that. It's going to go down here. Awesome. So that's your cone. It's if you can kind of see here, there's sort of like a triangle right here, right? And that's your Pythagorean theorem. All right. No more hypers. Actually, there's one more hyper. Elliptic paraboloid. So I just have to make this z not squared. I can do that in front of you guys. Just raise the z to the first power for each of these. That's pretty doable in a quick transformation here. Right, we already looked at the paraboloid. Right, you had a parabola parallel to the xz plane. These are parabolas parallel to the yz plane, and then it's ellipses parallel to the xy plane. All right. Last one is the hyperbolic paraboloid, the Pringle. And I guess we're just going to have a green Pringle, and that's just going to be what it is. And, you know, just deal with it. All right. There we go. So, yeah, I mean, the idea is that if you kind of observe here, you can kind of cut a little section off and make it look like a Pringle. I don't know. So this is a, what is it? What is a meme? It was a salted potato hyperbolic paraboloids. That's what Pringles are. I heard it a few times, that joke a few times over. So that is recycled. Anyway, yeah, you end up getting just kind of a fun shape that we end up using to talk about saddles. And then we'll address that when the time comes. Do you have to be a pro at these shapes? Absolutely not. But hopefully you're a little better at reading into them. That's it for now. Math on.